All right, so let's talk about ozone, stratospheric ozone versus tropospheric ozone. We're going to look at human health impacts, ecological impacts, how human activity can contribute to not only the depletion of the stratospheric ozone layer, but also the creation of tropospheric ozone, which is not good. So let's take a look at ozone in different levels of the atmosphere. First of all, stratospheric ozone is good, tropospheric ozone is bad. Tropospheric ozone basically is smog, but the ozone that's up in the stratosphere is super important simply because it absorbs ultraviolet radiation, UV, UVB, UVC ultraviolet radiation. So here is a pretty good diagram talking about not only the radiation that the ozone layer actually shields the Earth from, but it also goes a little bit into the CFC molecules and the ozone molecules, a little bit behind the chemistry. Notice down here on the bottom, you do have your ozone depleting chemicals. We're going to focus a lot today on CFCs, but here are some other ozone depleting chemicals that build up in the atmosphere and then eventually wind up leading to the destruction of stratospheric ozone. So some human health benefits from the ozone layer doing its job. Here you're seeing the negative. Certainly there's going to be a reduction in different types of skin cancer. There's going to be a reduction in sunburn. And there's also going to be a reduction in the rates of eye damage, things like cataracts. So these are some things that, that won't happen as much if the stratospheric ozone layer is in fact intact. So let's talk about the chemistry of UV absorption in the stratosphere. So basically what you need to realize is that we've got chemical decomposition of stratospheric ozone in the atmosphere. And then we've got the cycling around of these solo oxygen atoms. So the process is you've got O3 absorbing UV radiation, and it splits it into O2 and oxygen. And these free oxygen atoms are just kind of floating around, and they wind up latching on to another O2 that's also floating around. So it's this constant interconversion process. And what it's doing is not only are those O3 molecules being broken apart and then coming back together, basically what it's doing is it's converting UV radiation into thermal energy, which in turn heats the stratosphere. So we've got oxygen molecules reacting with an oxygen atom to form ozone because the ozone actually absorbs UV radiation. So as you can see with this diagram, it's actually a nice cyclical process. Now, ozone depletion, and here is an actual CFC molecule. What we've got is ultraviolet radiation causes a chlorine atom to break away from the CFC molecule. And then that chlorine atom actually winds up pulling an oxygen molecule away from an O3. Now, we know based on the previous slide, an oxygen atom that goes away from the O3 is supposed to be go through this whole big interconversion cyclical process of hooking back up with another O2 in order to be able to recycle the ozone based on the absorption of UV rays. But what we've got now is we've got a chlorine atom pulling an oxygen atom away. Then those free oxygens wind up reacting with the chlorine and oxygen, the chlorine monoxide molecule. And the result is what you get is you get an O2 plus another free chlorine atom. So you get this continuing cycle of chlorine atoms being created in the ozone layer. And free chlorine destroys stratospheric ozone. So it continues to kind of allow these single oxygen layers not to reform with O2s. It takes a single oxygen away from an O3, and then, as we can see here in step 4, or here's step 3, it takes a single oxygen away from an O3. Then here in step 4, those single oxygens here that should be hooking up with these O2s to create ozone wind up hooking up with this chlorine monoxide. Then the chlorine atom leaves, creating an O2. So you're reducing the number of these free oxygens that could combine with these O2 molecules to form ozone. Because what's happening is is that the free oxygen created by the breakdown of O3 during the normal process, they wind up getting hooked together by this chlorine atom. And as we said in class, a buildup of O2 does not absorb the ultraviolet radiation the way that O3 does. All right, so some things, actually I'm going to go back. Some things to worry about with regard to CFCs. As we can see here, the chlorine continues to stay in the atmosphere. CFCs take an awfully long time to migrate into the stratosphere. And when they're there, they have an awfully long lifetime in the stratosphere. And of course, even though protocols were set forth in Montreal in 1987, they were revisited at the Kyoto Convention in 1992. CFCs are continued to be used, especially in lesser developed countries. So you still have the penetration of CFCs into the atmosphere and into the stratosphere. All right, so here's tropospheric ozone formation. In the troposphere is a not good thing. There we're dealing with smog. Ground level ozone basically is a bunch of carbon monoxide, it's sulfur oxides. You got different particulates coming from all these different types of sources. You got nitrogen oxides, you got volatile organic compounds. All of that stuff combined with sunlight is going to create smog. So human activities that could lead to the formation of ozone would be burning fossil fuels like motor vehicle use, landscaping equipment use, electric power generation, industrial production, releasing these volatile organic compounds like pumping gas. When you pump gas into your car, you release volatile organic compounds. Using solvent-based paints is another way. And then tropospheric ozone levels will peak during the daytime simply because sunlight is required to form tropospheric ozone. And the tropospheric ozone is created because of photochemical reactions. Photo meaning light. All right, some negative impacts of tropospheric ozone. Okay, we're going to talk ecologically. So obviously what we're seeing here is we're seeing some plant tissue that's been damaged. Damaging plant tissue stresses them. It makes them more vulnerable to disease and pests. Thinking along the lines of animal life, it also irritates the respiratory system of animals. But it also reduces primary productivity. It inhibits photosynthesis. You inhibit or you reduce primary productivity, you're reducing all of that stuff at the base of the food chain, and it affects the rest of the food chain. And then, of course, ozone is a greenhouse gas, and it contributes to climate change. It's got a negative ecological impact. You could lose habitat, you could lose biodiversity, biomes could be shifted. So tropospheric ozone is a greenhouse gas, but it also can lead to warming and habitat loss or ecological change. Now, here's some impacts in terms of human health. Respiratory system problems. We've all seen pictures of people in China having to walk around their city wearing masks because of the effects of smog or tropospheric ozone. You got throat irritation, coughing, decreased lung function, diseases of the respiratory system, asthma, bronchitis, all of those things. Another thing that would be a negative human health thing would be eye irritation. It's all well and good that you've got plans in place to help you with regard to respiratory problems, but you also have to worry about the irritation of the eyes. And then, of course, again, greenhouse gas. Negative human health impacts because of global climate change. You're increasing the range of disease vectors. A warmer planet, warmer climates mean that some diseases are going to wind up thriving even more. You're going to have increased risk of harm from severe weather events, increased hunger because of decreased crop yields. So all of these things can be tied into stratospheric ozone versus tropospheric ozone. You've got human health aspects from a reduction in stratospheric ozone, that's skin cancer, sunburns, cataracts, eye damage. But then you also have these major impacts from tropospheric ozone as well. So I hope this gives you a little bit of insight into what the ozone layer is and the major difference between stratospheric and tropospheric ozone. Talk to you soon.